Hi, my name is Audrey and I go to Greenwich High School. I'd like to first thank CT-JSHS for this wonderful opportunity to present my research. My project is titled The Eco-Friendly Remediation of Polycyclic Aromatic Hydrocarbons in Stormwater via Magnesium-Infused Calcite Crystal Supramolecular Hydrogel Scaffolding. Polycyclic aromatic hydrocarbons, or PAHs, are organic compounds with two or more aromatic rings. They result from the incomplete combustion of fossil fuels and evaporation of petroleum products. PAHs are often found in stormwater runoff due to motor vehicle usage, oil spillage, and roadways, specifically coal tar-based pavement. As people are exposed to PAHs through the air they breathe in as well as food and water consumed, this leads to kidney and liver issues. Prolonged exposure and skin contact has been associated with cancer. Also, PAHs in water get absorbed and transported throughout the ecosystem, causing immunotoxicity and embryonic abnormalities when in contact with marine organisms. Clearly, there is a need for a water filtration system that can remove PAHs from running water in real time, as there are no current methods available. A paper written by Reddy et al. Stated that calcite is an effective PAH filter material. Further, Schra et al. Stated that magnesium reduces the time to remove PAHs in coal tar. However, these materials are static powders and can't be applied for running water remediation. That's why I proposed to integrate magnesium ions during calcite crystallization to optimize pH removal, and then enclose the Mg calcite in a calcium carbonate and polyacrylic acid hydrogel, synthesizing MgAPH, or the hydrogel system. The hydrogel system will then be placed in a 4-fold scaffolded water-permeable pouch to allow for enhanced interaction between magnesium calcite and the PAHs. During my literature search, phenanthrene and naphthalene were listed as PAH compounds commonly found in stormwater runoff. As they are also easily attainable, they were used as the model PAHs in my experiments. Phenanthrene has a solubility of 1.15 milligrams per liter, and naphthalene's is 33 milligrams per liter. First, I had to determine how to detect pH concentrations. Fluorescence is an ideal method as it is very sensitive even at low concentrations. The x-axes of these graphs represent the wavelength in nanometers, and the y-axes depict relative intensity. I discovered that phenanthrene has maximum fluorescence at a 235 nanometer excitation, resulting in a 360 nanometer emission. Naphthalene has maximum fluorescence at a 210 nanometer excitation, resulting in a 320 nanometer emission. In order to quantify the amount of PAHs in the solution, calibration curves were constructed. On the left are the fluorescence spectra of naphthalene emission intensities at a 320 nanometer emission. If I could draw your attention to the graph on the right, the x-axis is concentration of naphthalene and the y-axis is intensity. I measured serial dilutions of naphthalene solution, ranging from solubility level, 33 micrograms per milliliter, down to 5 micrograms per milliliter. This linear regression will be used to convert fluorescent intensity to naphthalene concentration. The same process was repeated for phenanthrene. The maximum intensities at a 360 nanometer emission were plotted against concentrations. The dilutions I made started at solubility level, 1.15 micrograms per milliliter, and ended at 0.1 micrograms per milliliter. Now that I knew how to quantify pH concentrations, I had to infuse magnesium into calcite crystals to create magnesium calcite, the component for pH removal. This was done by forming an aqueous solution from calcium chloride, magnesium chloride, and sodium carbonate. The Stowe method was followed with minor modifications. Magnesium calcite precipitated from the solution. On the left is an SEM of the magnesium calcite showing a uniform and regular appearance. The EDS I took of the Mg calcite on the right confirmed that magnesium was included in the calcite structure as circled. The hydrogel used to house the Mg calcite was formed from a solution of calcium carbonate and polyacrylic acid. The Sun method was followed with minor modifications. I then sonicated the ACC-PAA hydrogel with Mg calcite for 2 hours to synthesize the hydrogel system, or MgAPH. The x-axis of the FTIR on the left is wave numbers, and the y-axis is percent transmittance. The spectral peak at around 900 wave numbers is prominent evidence that the magnesium calcite was successfully included into the hydrogel. I also measured an SEM of a freeze-dried calcite hydrogel, which indicates that the gel has a highly porous structure with 5 micrometer pores, allowing for Mg calcite and water interaction. I wanted to get a feeling for how fast the hydrogel system could expand and start remediation, so I conducted this study by putting a known air-dried mass of the Mg calcite hydrogel in water. The x-axis of this graph is the time in minutes, and the y-axis is the water mass absorption per gram of MgAPH. There is a linear expansion in the first 20 minutes, with the gel reaching full expansion in 25 minutes. The mass from the dry to initial state increased 2.5 times, and this shows that once placed in water, the system will work rather rapidly. Next, I wanted to measure the remediation capability of Mg calcite hydrogel in saturated solutions. I noticed immediately these solutions outgassed very strongly. In order to determine the remediation efficiencies of the hydrogel system by itself, I needed to conduct my study in a closed system. Oddly enough, this wasn't really discussed in the literature I read. Regardless, I designed a closed system for pH remediation by the hydrogel. I used 10 milliliter airtight bottles filled to the rim with a saturated solution of phenanthrene or naphthalene. I put 200 milligrams of the hydrogel in one bottle, and the other had no hydrogel for control trials. At hourly intervals, a syringe was used to take around 3 milliliters of the solution out and to put it into a gas-tight cuvette, from which the fluorescent intensity was measured. The same syringe was then used to put the solution back into the bottle for continued testing, and this was done over a span of 5 hours. On the left are spectra from the naphthalene with hydrogel trials, along with examples of the bottles used. The x-axis of the graph on the right is the time in minutes, and the y-axis is the amount of naphthalene present in micrograms. The blue line represents the control bottle, which stayed constant due to the airtight environment. The green line is the theoretical amount of PAH removal that can be done by 70 milligrams of Mg calcite, and the red line is the Mg calcite with hydrogel trials. The red line gets really close to the green after 300 minutes, and the hydrogel was found to achieve 92% efficiency and was able to remediate 140 micrograms of naphthalene per gram of hydrogel used. The same trials were run with phenanthrene. Again, the control stayed constant, and the Mg calcite hydrogel achieved 82% efficiency compared to the expected remediation of free Mg calcite, corresponding to 5.5 micrograms of phenanthrene removed per gram of hydrogel. When I took infrared spectra of the used hydrogel systems, there was a growth of the spectral peak at 772 wave numbers in both used gels from phenanthrene and naphthalene solutions. It's difficult to get an accurate measurement of how much pHs are being remediated in flowing water. However, since the pHs are detectable in the hydrogel system, this provides an opportunity to measure pH remediation in a flowing system not by collecting flowing water samples, but by analysis of the hydrogel device itself and the increase of spectral peaks. Now that the efficiency of the Mg calcite hydrogel was established, it was time to implement the scaffold design. This was done by sewing 4 layers of water-permeable cloth together and putting hydrogel in each of the 3 compartments, with a total hydrogel surface area of 15 centimeters squared. The pouch was sealed on all sides, creating the remediation device. On the right is my vision for how the pouch would function with increased surface area in a body of water. Here are diagrams for how I propose the hydrogel system should be used, either attached to the shoreline or placed midstream. As mentioned earlier, since water is just flowing past, it's useful to know that the pH capture can be measured with an FTIR of the gel. To measure that type of application, a tube system with a pump was used. On the left is a photo of the setup. The flow rate was 1.4 liters to scale, simulating a midstream placement. The pouch totaled around 10 grams, with 8.3 grams being Mg calcite hydrogel. Here is a closer look at the scaffolded pouch. And you can clearly see the water flowing past. To fill the system, I used 2.8 liters of saturated phenanthrene or naphthalene solution. Over a course of 5 hours.
2 minutes.
What? Oh, thank you.
2
4
minutes.
milliliters were drawn each hour to determine fluorescent intensity. As the system was open, I also conducted control methods to account for pH outgassing. The x-axis on this graph is the time in hours, and the y-axis is the naphthalene concentration in micrograms per milliliter. The red line is the loss of naphthalene due to outgassing, and the difference of the two curves is the amount of naphthalene remediated by the gel alone, which equaled 38.26 milligrams. This corresponds to 4.6 milligrams of naphthalene removed per gram of scaffolded Mg calcite hydrogel. To compare with the static experiment, the efficiency rate improved 16 times, solely due to scaffolding. Here are the results for phenanthrene. Taking into account the outgassing from the control trials, the hydrogel removed 0.97 milligrams of phenanthrene, corresponding to 0.12 milligrams of phenanthrene remediated per gram of Mg calcite hydrogel used. Similarly, the rate improved around 11 times compared to the previous airtight experiment, highlighting that the scaffold design optimizes pH removal. Finally, a stability study was conducted by putting a 10-gram hydrogel pouch in 250 milliliters of water. 15 microliters of the water were drawn at hourly intervals, and the infrared spectrum of its dry film was measured, and this study was done over a 5-hour period. When compared with the spectra of the components in the hydrogel system, the surrounding water's dry film indicated that there was no ingredient degradation of the pouch. This shows that the Mg calcite hydrogel is stable in water and can be used for pH removal without other effects on the ecosystem. To conclude, an easily producible and environmentally friendly filtration device was made from a calcium carbonate and polyacrylic acid hydrogel with Mg calcite embedded in it. This system demonstrates success in both controlled and proposed streamflow settings with a scaffolded pouch. Also, the scaffolding design improved efficiency rates by 16 and 11 times respectively for naphthalene and phenanthrene. Once the system has reached its full usage, the hydrogel can simply and safely be taken out and disposed of at an appropriate waste station. The scaffolded hydrogel system has a cost. Okay, thank you. And if I may quickly, here are just my acknowledgements and references. Thank you for listening, and I'd be happy to answer any questions.